Okay, so I'm going to talk about a theoretical computer science approach to consciousness and artificial general intelligence. And theoretical computer science is a branch of mathematics concerned with understanding the underlying principles of computation and complexity, including the implications of resource limitations, particularly time and space. And we're going to define a conscious Turing machine, which I think this morning Ron allowed me to do. A simple formal machine model for the purpose of investigating a TCS approach to consciousness. And for this, we're hewn to the TCS demand for simplicity. We're looking for minimal assumptions. We're looking for formal definitions, and hopefully we can yield at least high-level explanations and predictions from our model. So here's an outline of my talk today. I'll give a brief introduction. I'm going to say what the Conscious Turing Machine is not. I'm going to talk about the structure of the CTM and its dynamics. I'm going to talk a lot about the competition, the uptree competition, because it has very nice properties, which we're quite proud of. And then I'll talk about the definition of conscious attention in the CTM and feelings of consciousness in the CTM. And towards the end, I'll talk about alignment with other theories and models of consciousness, and then end with CTM as a model for AGI. And maybe if I have enough time, talk about some work in progress. Okay. So the Conscious Turing Machine is inspired by Alan Turing's simple yet powerful model of computation, the Turing machine. And here we have a 23-state universal Turing machine, which can compute any computable function. Okay, and we're also inspired by Bernard Bahr's global workspace theory of consciousness, the theater model. And here's Bahr's and the theater of consciousness. There is some history here, though. The theater model actually goes back, at least, probably goes back to Plato, but in the 19th century, the French philosopher Taine talked about the theater model, and global workspace really originated at our institution, Carnegie Mellon, with Newell and Simon and Rodretti, who looked at global workspace for cognition. And then it was picked up by neuroscientists, Changeau, Dehaene, Nakash, Sargent, who look at the neural correlates. So it's the global neural workspace theory. Okay. So Bahr's describes conscious awareness or conscious attention through a theater analogy. And he says consciousness is the activity of actors in a play performing on a stage of working or short-term memory. The inner speech actor is often on stage. And the performance is under observation by a huge audience of unconscious processors in long-term memory that are sitting in the dark. So you're the unconscious processors there, and the unconscious processors vie amongst themselves to get their scripts or their query or their information on stage to be broadcast to the rest of the audience. Okay, and I think I like this example because it really shows, for me at least, the theater model. So I don't know if this has happened to you, but it's happened to me a lot, that you're at a party, you see somebody you know, but for the life of you, you can't remember their name. Happened to you? But then you go home a half hour later, your name pops up, right? When it's too late, you want to make a date, you want to see them again, too late. Okay, so what's going on there? There's a processor there that's very embarrassed in long-term memory, and it's saying, what's her name? And it's putting a lot of weight to that question, and it gets up into short-term memory on the stage, and it gets broadcast down to all your long-term memory processors. And one of those processors, after a while, will pop up, they'll recall where you first met, and you might be at the ASSC meeting a few weeks ago in New York, and that gets broadcast down. And something of what she does, well, she works into consciousness. That gets up to short-term memory, gets broadcast down. And then a processor say, oh, I know her name starts with T, and that gets broadcast down. But an hour later, her name, which is Aida, gets up to the stage from the audience, which has been thinking, searching. And we'll talk about that disconnect between T and Aida in a little bit. Okay, so the conscious self on stage doesn't know how or where her name is found. The conscious self is not privy to the workings of the unconscious self, and I sometimes call this the Poincaré effect, and if you want to know what that is, I'll talk about it later. Okay, so before I go into the structure and the dynamics of the conscious Turing machine, I'd like to say what it is not, okay? It is not a model of the brain. It's a simple, formal machine model of consciousness. It considers the brain at a very high level of abstraction, at levels well above that of neurons and neuronal activity, so it's well above the fray. It's not a standard Turing machine, and it's not even a Turing machine. What gives the CTM the feeling of consciousness is not its input-output map, and it's not its computing power, but what's under the hood. And what's under the hood is the global workspace, its interaction with its environment, including itself. It's something we call predictive dynamics, which are cycles of prediction, feedback, and learning. And some key processors like inner speech processors, sensation processors, and model of the world processors that communicate to each other within a multimodal language, which we call brainish. Okay, attention is paid to resource limitations with respect to its construction and explanations. And in fact, that computation takes time is important in the construction. Okay, the CTM is not even a standard global workspace model. There are important differences between Barr's model and ours. For example, CTM has a well-defined competition for global workspace access, how the audience members get their information on stage. CTM's subjective feelings of consciousness result from interactions between its evolving world models and its global workspace. And the CTM has no central executive. And that's making it a good model for AGI, and hopefully we'll get to that why later, okay? So here I'm gonna go. This first page is full of just notation, but just bear with me, and then we'll go to pictures very quickly. Okay, the CTM is a 7-tuple. It consists of STM, LTM, uptree, downtree, links, input, output. Time is measured in discrete clock ticks, t equals 0, 1, 2, up to t, which is about 10 to the 10th for our model. The CTM is born at time 0, and it has a finite lifetime t. STM up there is a small memory capable of holding a single chunk, and very soon I'll formally define what we mean by chunk. LTM is a massive parallel collection of N, capital N, powerful processors, and here N is greater than, it's a large number, like greater than 10 to the 7th. The uptree is an upward-directed binary tree of height h with N leaves, 1 leaf in each LTM processor, and a single root in STM. The downtree is a simple down-directed tree of height 1 with a single root in STM and N edges directed from that root to the leaves, 1 leaf in each LTM processor. Links are channels for transmitting information between processors. Then we have, for each time t, there's an input map, which is dependent on t from Rn to the long-term memory processors via sensors. There are output maps at each time t from long-term memories to the outside world via actuators. On Rm is CTM's external world, R is the real numbers, M is positive integer dimension, T and A are non-negative integers. And T is a non-negative integer, and that's time. Okay, you can sort of forget this now because I'm going to go into pictures. And so, but if you're going to formally define it, that's how we'd go, and we just give definitions and theorems and all that, but I'm not going to do it that way. So, okay, so here's, we're going to do it again. The whole thing through via pictures. Okay, so we start with a very tiny short-term memory. That's our stage. And this stage can hold 1 chunk of information, and as I said, we'll formally define chunks shortly. It's not George Miller's 7 plus or minus 2, but just 1 chunk, but we can get away with 1. We're looking for simplicity, so 1 will do for us. It has a very large number, I said more than 10 to the 7th, parallel powerful processors. Those are what we call long-term memory processors. All processors are long-term memory processor, an LTM, for our machine. And that's our audience, okay? And we have input coming from the external world via sensors of the eyes, ears, nose, mouth, going to special long-term memory processors. And then we have output coming from some of the long-term memories directly to actuators like feet, talking, singing, to affect the outside world. Okay, so there we've gone through STM, LTM, input map, output map, here in pictures. And then at each moment of time, every processor puts a chunk of information into a competition, an uptree competition to get onto the stage. And so once a chunk gets on stage, we call it the conscious content at time t in our, that's just our definition, the conscious content in the conscious Turing machine of that chunk. And as soon as it gets in, it is broadcast via the downtree to all long-term memory processors. And when that happens, we start by saying the conscious attention in CTM at time t+1 is the reception by all long-term memory processors of the broadcast of CTM's conscious content. So in other words, the conscious content we call is the one that's on the stage, but as soon as it gets broadcast, we say CTM is paying conscious attention to whatever that information was when they receive that. Now, I'll go into the uptree competition shortly. It'll take more time than coming down. So there is a little delay. Maybe if we use the right time, it's like 200 milliseconds between going from unconscious to get into short-term memory and down again. And this is a little like Libet. There is a time lapse between an unconscious thought becoming conscious in the CTM in this model. Okay, so links, as I said at the beginning, all of these processes are independent. They're not connected at all. But every so often, when one processor sees that another processor has like-minded information, it will form a link. So the processor that said, "What's her name?" Then finally got the answer. Her name was Aida. It'll form a link together. And that's how links grow. And what links do is they have a nice property. What they do is they turn a conscious computation or communication into unconscious communication. So at first, all the communication has to go through short-term memory. There are no links at all. Everything's conscious. The long-term memory processors pay attention to it, conscious attention. But after a while, links form and information can flow unconsciously. So this is sort of what happens. Well, before I'm still going ahead of myself, how do they communicate? Okay, so the processors have their own language. They work their own independent way, but they have a communal language we call Brainish, which is a rich multimodal inner language. And this language is, instead of just having words, each word in Brainish really is a multimodal word. It connects images, maybe sounds, sensations, smells. So for example, a word for rose might be a picture of a rose, the pinkness of a rose, the color, the sweet smell, the touch, the smooth touch of a rose. That would be all connected, fused together in a Brainish word. And in fact, Paul Yang, who we're working with, is developing Brainish for computer systems. Okay, right. So links turn conscious communication, as I mentioned, going through short-term memory, to unconscious communication via links using Brainish language through processors. And for example, when you're learning to ride a bike, at first, everybody has to pay attention, conscious attention, to all of your movements when you're going right and left, when your parents taught you how you were doing that. But very soon, all of those movements, all of those things that you have to do become unconscious. And mostly when you're riding a bike now, you're not thinking about what you're doing. Everything's happening, except if you're startled, whatever. Everything's done unconsciously. Alison Gupnick, who's a child psychologist, likes to say that babies are more conscious than adults, which sounds a little bit peculiar. And we can interpret in our machine that baby conscious Turing machines are more conscious than adult CTMs with respect to conscious attention. We're not talking about conscious feeling, but conscious attention now. Because at the beginning, everything has to go through short-term memory. Everything's conscious. They're paying attention to a lot of different things they're paying a conscious attention to. But now they don't have all the conscious awareness type of feelings that we have. So there's a different kind of consciousness, which we'll talk about shortly. But in terms of conscious attention, Alison Gupnick's saying makes sense to us in the CTM. Okay, I'm going to say a little bit more about the long-term memory processors. In our yes, was there a question? Okay. In our formal model at time t equals 0, all long-term memory processors are generic with certain basic built-in properties. There are some built-in learning algorithms. They have a tendency to go for positive rather than negative. And the functionality of the processes will emerge over time. But for now, and in this talk, we designate some important LTM processes built in, like the model of the world processor we're going to build in right now, and allow for off-the-shelf processors. Why not put ChatGPT in as one of the long-term memory processes? It's easy to do. Put it in. Okay. Also, processors may also have functions analogous to brain processes like the visual cortex, hippocampus, thalamus, amygdala, reticular formation. No reason they can't have a sort of analogous type of properties. And as I mentioned, there are built-in learning algorithms in all of our processors. And one of the important ones for us is what's called the sleeping experts learning algorithms. And I know Manuel was just telling somebody that when we were doing this, we were talking to Lenore Blum, who happens to be our son, and he's a machine learning guy. And we told him that we really needed something to have a balance for our processes to balance what they're doing. They can't go off the scale and always say, my thing is so important, I'm going to put very high weight. We need to balance the system. And he says, I have just what you need. It's called the sleeping experts learning algorithm. And what the sleeping experts learning algorithm does, remember at the beginning, what's her name? And there was a processor that said her name started with T, but actually her name was Aida. So its sleeping expert algorithm will say, hey, you were too bold. You gave too much weight to your answer. You got into the stage, but you were wrong. Her name was Aida. Next time, lower your weight a little bit. And then there might have been a processor who really said her name was Aida, but that processor was too timid, didn't give enough weight, and so its information didn't get in right away into short-term memory. And so its sleeping expert algorithm would say, hey, why don't you boost yourself a little bit? Next time, give a little bit more weight to your chunk, what you're putting in. So the sleeping expert algorithm will embolden its processor if its chunk did not get into CTM and its information is more valuable in the CAA's opinion than what got into STM. And the sleeping expert algorithm will hush its processor if the chunk got into STM and the information in chunk is found, maybe at some later time, to be less valuable than that of another chunk that failed to get into STM. Okay. So right away, you can see something called, in a global fashion, what we call predictive dynamics, cycles of prediction, feedback, and learning. So when processes put chunks into the competition, that's like a prediction. When some of the processors tell some actuators to do something, that's a prediction. When some processor communicates to another processor via link, that's a prediction. It's getting feedback from the broadcast. They're getting feedback from input from the external world, and they're getting feedback from other processors via links. And internally, we have the sleeping expert algorithms, and internally, there are other learning algorithms. So we have these cycles globally and actually locally amongst the processors of this sort of cycles of prediction, feedback, and learning going on. Okay, so now I said I'm going to spend more time, which I never do, but I thought it was instructive to do this, to spend more time in our up-tree competition. Because nobody ever says how this information would get into short-term memory. So as I said, at each moment in time, each long-term memory processor puts a chunk into the competition. And we have a formal definition of chunk. Okay, chunk is often defined very informally. It's a little bit of information, maybe a phrase, maybe something, a poem. But we're formally defining it as a 6-tuple. So when a processor P puts a chunk in, it gives 6 parts of information. The first is its address. Okay, they're 10 to the 7th processors. It's a 7-digit number, not too large. The time the chunk was put in, the gist, which is the most important part, which is succinct information in brainish of what information, like the query, what's her name, or her name is Aida, or begins with T, or something like that. That's part of the gist. And it also gives a weight, and the weight happens to be a valence number, so it could be positive or negative, and it's somehow the processor's value of the importance of the chunk of information that it's giving. So remember, T gave too much value, too large a number. And then the last two parameters here in green start off as intensity starts off as the absolute value of the weight, and mood starts off as weight, okay? And as a chunk goes up, we have a competition tree. As it goes up, the first 4 parameters will stay the same. The last 2 will change, and that's very important. So let's watch and see what happens here. So chunks are going to complete locally, and the local winner moves up the tree 1 level. So I'm going to show you how this process works. Okay, so here we have 2 chunks, C1 and C2, and they've come up to a certain level, and we want to know how the winner at the next level is chosen. Okay? Okay, now up to this point, everything I said was deterministic. Okay? But we were having real trouble with the competition tree and others in the determinants. We could do it, but it was very kludgy and all that. And we realized if we added a little probability, made everything totally simple. So from now on, we have a probabilistic CTM. And so we've added in the competition up tree at each node what we call a coin flip out neuron. And it's just if it takes in A and B, then it'll output A with probably A over A plus B, and B the reverse. Okay? Okay, so let me tell you now how the process is going to work. Okay, and I'm going to start with a simple competition function, and the competition function will be just measuring the intensity, the local intensity of the chunk. So it'll look through that whole 6-tuple, and it'll look at the intensity, and that's will be the function it's looking at. Okay, and the algorithm will be the following. Given competing chunks C1 and C2, which you have there, input the intensity of C1, because we're using intensity now, and the intensity of C2 into the coin flip neuron. And then CI is the local winner with the probability, its intensity over the sum of the 2 intensities below. Okay, that will be our algorithm. And the winner will be, with that same probability, will have the same first 4 as the one that has the high probability of winning. And the last 2 will be just the sum of the 2 intensities of the current ones and the sum of the 2 moods of the current one. So now the moods and intensities are changing, but the winner keeps the first 4 parameters there. And we'll see what happens now. And if by doing a little induction, we can see what happens here is that the probability of a chunk C winning the competition will just be its intensity over the sum of the intensities. And that's very nice because it's independent of the location of the processor, which is very nice because we don't want to have to move processes around in a machine each time we have a competition. We want to we want stability, and we don't want to move processes in our head around a lot either. So this is a very nice property of this. And this is the question that everybody asks us, so I'll point to it now. Why don't we just more simply just compute the sum of all the intensities, broadcast the sum to all processors, let processors compute their own probability, and let processors choose the winner probabilistically, okay? Well, as you can see, it's not as simple as that appears, because we have capital N, more than 10 to the 7th intensities that we have to compute, get it up there, project it down. So our competition is in fact doing that very efficiently. It's it's a binary tree. It's doing that very efficiently locally. So no processor has to know about the other information. It's all done, everything's done very locally. Okay, so that's one of the importance. You can't really do the other. And why is it important to have a simple solution? Because it's one of the things that convinces us that we're on the right track. Okay, so now I'm going to make a couple of comments. So when that winner gets up to the top, actually, and it's projected down to all the processors, those processors get quite a bit of information. Let me tell you what they get. So they get which processor won, that's the address, right, because that's going to be projected down, the time the chunk was put in, the gist that won, and the weight that was given. It's also getting the sum of the intensities, because as you go up, you're going to get all the sum of the intensities and the sum of the moods. So in addition to receiving the winning gist, weight, and all processors receive the address, and they can easily calculate the average intensity, the average mood of all chunks. So they're getting some global information immediately, as well as their own probability of winning. So they can incorporate all of this also in making decisions. So they are getting a lot of global information from the winner. Okay. So I want to, again, give a little simple example of why we like this competition function. And I said it's independent of location. And I'm going to compare it with a very simple tennis tournament. So, in tennis tournaments, they give ranks to players. And on the left-hand side, on the right-hand side, I have players A, B, C, and D, A, B, C, and D. And in the tennis tournament, the ranking, we have A, B, and D have ranking 1, and C has ranking 0. We have the same thing with intensities on the right-hand side, okay, for the CTM. But now look, player D on the left in the tennis, you'd like to be player D, right? Who would not like to be player D? Player D is playing, somebody has rank 0. They're going to have a half a chance of winning the next thing. So they're going to have a more probability of, getting, so player D actually has a half chance of winning the whole thing, whereas player A was unlucky because at first player A was playing player B with a high rank. So its probability of winning is 1/4. But on the other hand, if you look at what's happening in the CTM competition, because we're adding intensities, so we're actually sort of changing the rank, player A now has an advantage of having an intensity of 2 now versus 1 of player D at that time. And so at the first level, it's 1/2 probability, but then it gets a much higher probability at the second level, and its total probability is the third. Same as player D. If you look at the computation, player D is 1/3, and player B will also come out with 1/3. So independent of location. Nice feature. But now let me give you the general competition function. And it's a little bit, it includes intensity and mood and some parameters. And I'm just going to focus on the parameter D there. Okay. And we'll have the same with this more general one. We'll have a very similar results as with the simple one. The probability of a chunk winning will be just the F of that chunk over the sum. Okay, same sort of thing. Will be independent of a location. But what's really nice about this is a very general property of this particular general competition function. So if we look at what we call additive competition functions of intensity and mood, then the probability of a chunk winning is independent of a location of a processor, if and only if that's the function. So this function, this general function, it's kind of unique with that property under certain conditions. So we're feeling pretty confident that that's a really nice general competition function to get up there. But it even has some other nice properties, and I'm going to get into that now. So that coefficient d times the mood is what we call CTM's disposition. I'm using a kind of a human word here, okay? CTM's disposition, and you'll see why I'm using it in a few minutes. Okay, and so each CTM has a built-in d, fixed but not specified for now. And we'll say that CTM is level-headed if d is 0. So if d is 0, we're back in the first case that I showed you. It's essentially just the intensity. Okay? And we'll say CTM is optimistic if d is positive, if the disposition is positive. Manic if the disposition is +1. Pessimistic if the disposition is negative. Depressed if d is -1. Okay. But these definitions are not arbitrary. They might look like we just chose them that way, but they're not. And let me just go through and show you why, some implications. So suppose CTM is optimistic. In other words, d is positive, okay? Then what happens if a positive weighted chunk, its mood will be positive, right? So if we add d positive times the mood plus intensity, that will give a larger positive number. So positive weighted chunks will have a higher probability of winning than expected. And negative weighted chunks, you see the mood will be negative, that's the same as the weight. D is positive, that'll be a smaller number, intensity, which is the absolute value of the weight. So we'll have a smaller number there. So negative weighted chunks will have a lower probability. And it's known that generally optimistic humans have a longer lifetime than pessimistic humans, and general optimism in the CTM corresponds to D in the range between 0 and 1. And then if CTM is manic, in other words, we say D is +1, look what happens. As long as one chunk is positive, see, if a chunk is negative weight, its F value will be 0 because the intensity plus a negative number times its mood will be, so if it's a negative number between 0 and 1, it'll subtract out and it'll be a smaller number. Intensity plus d times the mood will be smaller than the intensity. So as long as one chunk is positive, and in fact, it'll be quite 0 because the mood and the intensity will cancel out exactly when d is +1. So as long as one chunk has positive weight, then the winning chunk will have positive weight, and CTM will not pay attention to any chunk that has negative weight. And if no chunk has positive weight, then CTM will flit around, because if no chunk has positive weight, all of them have negative weight. Intensity plus 1 times the mood will be 0. All zeros, they'll each have half probability going up. It'll flit around between all sorts of negative thoughts. So in other words, if there's only one thing positive, that manic CTM will hang on to it. And it will go into a real deep depression if there's not a single thing. So it's like manic depressive. It will go into a really flitting around between lots of negative thoughts if there's not a single thing that's positive. But it'll hang on to any positive thing in its life. So that's what mania is in our machine. And for depression, if the CTM is pessimistic, and that means the disposition is negative, then the thing reverses. Negative weighted chunks will have a higher probability because we'll have an addition up there of winning than expected. And if it's totally depressed, if D is -1, then if at least one chunk has a negative weight, then the winning chunk will have a negative weight because all the positive chunks will go to 0 in F. And the CTM will not pay attention to anything positive thoughts. And in fact, it's going to be very hard to get out of that state because if just one negative thought will keep somebody in that state. And it's known with humans that the only way to get out of these deep depressions is with electrotherapy, shock therapy, or drugs. Okay, so I'm going to skip this. Okay, so we have some definitions here. We have some things about our conscious Turing machine competition functions. We've considered the CTM experiences of other phenomena generally associated with consciousness. I've talked a lot about blind sight, unintentional blindness, change blindness. We've talked about dreams, pains, and then we'll mention free will. And this explanation is given for the CTM agree, at least at the high level, with cognitive neuroscience literature. And I've talked extensively about these three examples, blind sight, so I'm not going to go into them, but let me just refer to them. In blind sight, we have a person who claims they're blind, but nevertheless can get up and move around in a fairly reasonable way. And I know there are a lot of explanations, and Paul has a different one that we have, but at least the CTM can experience this, and let me show you how the CTM can experience this. So here's this guy sitting in a room, a cluttered room, and he's asked to go through the door. Maybe there's a meal on the other side. And he says, but he can't see. Nevertheless, he gets up and walks through the door. So what's going on? So in our CTM, what's happening, there's input coming from the eye to the vision processor. And at one time, we're assuming this guy could see. And so there's a link to the motor processor, and the motor processor can tell the leg to move. Unfortunately, the up tree to STM is broken, so there's no message going up to STM that I can see, so the guy has no conscious sense that he can see there. But nevertheless, he can move in some ways by prior links there. Then there's another example here that's often given in psychology classes. You're shown a film. You're asked to count the number of times the white-shirted players are passing the ball. Everybody's paying attention. They say 15 times, and then they're asked, did you see the gorilla? And there's a gorilla in plain sight. And okay, so what's happening? Our CTM will behave the same way. Why didn't the CTM see the gorilla, which is in plain sight? When the CTM is given a task, its processor gives higher weights to the task, those shirts in white, and probably won't be conscious of other things that are given lower weights. So it'll really pay attention, conscious attention to the white and not see the black or the gorilla. And change blindness, this comes from a film that's used, I think, in London to tell drivers to be careful of bicyclists. And it shows a scene at the beginning. A detective comes into a room, sees a dead guy on the floor. He very cleverly, quickly determines who actually killed the guy by knowing when petunias were planted at the wrong time. And then everybody's kind of startled at the end. But the big change is, why didn't people in the film see in the film that there were huge changes from the first scene to the last scene? So the detective's coat's changed, the dead guy's foot's off the floor, flowers have changed, so many things have changed. And partly the answer is that the filmmaker cleverly distracts us during the film by every so often focusing on different people, not seeing the transitions. And so all we could keep in our head was the short gist of the first scene and the last scene, but it's the same gist. The scene is the living room of a mansion with a butler, maid, and detective, and a man laid out on the floor. It's the same gist. That's why we weren't detecting it, and that's why our CTM wouldn't detect it, because it just has this short chunk, which is in short-term memory, that it's keeping. Okay, so we give explanations like that for many phenomena that's often associated with consciousness, at least in our CTM can experience them. Okay, so now in the last part, I want to say, why would a robot with a CTM brain feel conscious? So we've talked about conscious attention, which people sort of seem okay with. Now let's talk about feeling conscious. Okay. So we're claiming that the ability to create and utilize world models is key to CTM's feelings of consciousness. And so I'll talk a lot about the real model in terms of subjective feelings, but not one size fits all. Different subjective experiences will manifest in different ways. For example, pain versus pleasure will be very different. We could talk a little bit about extreme pain. May not be the exact solution to extreme pain, but is an actor that hogs the stage and it prevents all other actors from coming on, and that feels you can't do anything at all, so you're feeling pain. And so the weight of the pain processor's gist is very high, and it hogs the stage. And here this guy, maybe he's faking it, maybe not. But anyway, he can't do anything, and he's in extreme pain. Everybody sees his extreme pain. Okay. Pleasure's a little different. A mother's love, the alleviation of pain. Early on, a child or a CTM knows that either built in or by experience that negative moods are to be avoided. They learn that they can lessen a negative mood by seeking a positive mood, like getting milk. On the other hand, they do not learn in general to avoid positive moods. So in this way, positive and negative moods are not symmetric. And we hypothesize that a system such as CTM built to attain homeostasis via its inherent predictive dynamics will have feelings of pleasure and well-being in its quest to attain that goal. That's sort of consistent with some of the literature on pleasure. But even though there are different explanations, I'm claiming, and maybe we claim, that predictive dynamics actually underlies all of these explanations. Okay, so let's look at the CTM from the point of view of the model of the world processor. And here on the right-hand side, I have the world. And here on the left-hand side is the model of the world processor has made some sort of caricature of the world, okay? It has some pictures in there, and it has its inner world, and it has the outer world. And the model of the world processor maintains models of the world and of the CTM in its world. And the processor serves many purposes. It figures in explorations and exploitations of its world and in planning in general. It's how the CTM understands itself and its place in the world. It accomplishes its role, and this is very important, through its interaction with the other processors, consciously or unconsciously. It's getting feedback also, and it's asking questions of other processors, consciously or unconsciously, and makes predictions, and it's asking, like the motor processor, to do something to see if things happen, and it's updating given feedback. So it's constantly interacting with the other processors. And it tags elements in its various models of the world with multimodal brainish gists, including labeling actuators as self when it consistently detects them carry out its requests. So it might say the leg is a thing. And I think this is a very good demonstration with this baby, who is actually sort of seeing that by power of thought. He's moving his leg. He's sort of seeing that it's part of it. And he's starting to realize itself. And if you'll see very shortly, he's actually trying to look at the other leg to see if he can do it. I don't think he can quite do it yet. But he's certainly labeling his left leg as self. He might even label the bottle at first as self because he cries, and then he gets the bottle right away. Maybe that's self. So at the beginning, he may be making mistakes like that as well. So again, I want to emphasize the model of the world accomplishes its roles through its interactions with other processors, consciously or unconsciously, by making predictions and updating given feedback. And here our CTM decided to play football, okay? And it actually suffered some dire accident. And there it is, like there. And again, it's interacting. It's sort of not letting any other. Its pain processor is not letting any other anything into STM, so nothing can happen. It's paralyzed, and it's saying, oh, that must be extreme pain, and it's feeling extreme pains. So when the model of world detects the CTM paying attention, remember I had paying attention when all the processors get information, it tags the CTM in its model as consciously aware. So that's what we've sort of changed. Consciously aware is when the model of the world understands that the CTM is paying attention. So it's consciously aware. And this is our definition of conscious awareness in the CTM. And then when the model of the world processor detects the CTM thinking about its own consciousness, it tags CTM in its model of the world as conscious. And looking at the CTM from the viewpoint of the outside world, we see something about the CTM. Specifically, the CTM considers itself conscious. And what is conscious cannot be the model of the world processor or any other processor, because processors have no feelings. They are just machines running algorithms. And we're proposing that the view, the CTM as a whole, feels it is conscious as a consequence, in part, of the fact that the model of the world processor views the CTM in its model of the world as conscious, and this view is broadcast to all processors, in particular processes that are important that deal with the feelings. And this is kindred in spirit to Michael Graziano's attention schema theory of consciousness. 5 minutes, okay. Let me mention a few things about consequences of mislabeling. So Cotard syndrome happens when people start to label themselves as dead. And one can imagine certain processes happening that will cause the model of the world to label itself dead. That would be sort of some kind of very bad phenomena here. Body integrity disorder would be when our internal models of the world are labeling some of our features as not us, not self. And also delusional disorders. This CTM is thinking of me as a spy. Okay, so it has some delusional disorders, maybe. Okay, how do we check the correctness of this model? I'm not going to go into this too much. What I want to do is say the alignment with other models. So I guess when everybody has a theory of consciousness now, you're always getting some critiques. And some of the critiques that we've gotten have been like, well, what's new? We have global workspace model. You have that. We all will know AST, Graziano's attention. What are you doing that's new? So we're claiming that this is positive that our model aligns with life, because it's a very simple model, and yet it aligns with many things. So I'd like to say it aligns with attention schema theory. I've just talked about that. It aligns with predictive processing and recurrent processing. Our predictive dynamics has elements of that theory. It aligns with embodied, embedded, and extended mind theories. The sensors and actuators are its embodiedness. It aligns with embedded. Its interaction with the outside world is embedded. We're allowing off-the-shelf processes, gives it extended mind. It aligns with IIT because its feedback and interconnections in the system gives it high-fi. And it also aligns with the extended reticular dynamic activating system in free energy. I've recently started looking at Mark Soames' theory of consciousness. It's very interesting. Soames says that the source of consciousness is the brainstem. In other words, the extended reticular dynamic activating system. And he claims that's the source of consciousness, having the feelings, our homostats. So there's nothing to preclude the CTM from having long-term processors that function as these extended reticular activating system. And feelings acts as homeostasis. And then he tries to connect his theory, and he, together with Friston, connect it with the free energy principle by showing that, in fact, when in the brain you have a system of internal states, and you have external states, and then you have sensory states, and you have action states, and the action states and sensory states form a Markov blanket separating the internal from the external. The internal has to get ideas from the external through these, the sensory input and the action output. So I was a little curious here. So that's the blanket. And then once you have a blanket in a certain system, you'll get homeostasis, self-organizing, all of that nice features. That's a whole other theory I'm starting to learn about. But I was just curious to see how the STM set up here. So I noticed that there is a nice Markov blanket here. We have internal states. We have external states. We have sensory states, so there are sensors. We have active states. We have external information coming in through the sensors to the internal, going out to the active states, going to the external world. And I took their picture and flipped it around, and of course it looks exactly the same, topologically. So I think that there's the blanket there. So it's a bit of a stretch, but it's evocative. And I'd say our CTM algorithms are similar to that. And so we've gone through this. Quantum consciousness, I don't know at all. But yesterday, Tim Palmer gave me the out and showed that some old work of mine connects with Penrose's theory of quantum. But anyway, I think that's a long stretch as well, so I don't think there's anything there. I also see that a lot of our theory connects with the archival list of indicators for consciousness. And we can go through all of them, and almost everything except high-order theories we can check off. So that's it. And my punchline. Do I have time for 5 minutes?
Sure,
2 minutes?
absolutely.
Okay. So far I've talked about alignment. Now I want to talk about disalignment with bars. So we have a lot of alignment with bars, the stage, the LTM processors, but we have some major differences. There are no specific methods for LTM to get information to STM in bars. We have a well-defined competition. There's no model of the world in bars. We have a model of world here. But bars has a central executive, and we do not. No central executive, okay? In fact, the CTM you can think of as a federated ecosystem. There's no central executive doing things. Things are bubbling up. That's how decisions are made. And in fact, we're saying this is that consciousness is a prediction of ours, does not need a central executive. And we're in fact saying it has advantages for AGI, artificial general intelligence. And let me just give you an example. So here I'm a theoretical computer science, and I might say, I really want to know P equal NP. Right. So I'm one of the processors, and I put a huge amount of weight on it. It finally gets into short-term memory, and it gets broadcast down. And then the ChatGPT processor says, hey, folks, if you're interested in this problem, I'll give you some background on it. I'll tell you things that are known about it, what kinds of mathematics is being used to develop it or to understand it. That'll get up into short-term memory, go down, and then a processor will say, hey, I don't see that they're using topological methods, algebraic topology. Maybe I'm interested, get that information up there, it'll be broadcast, a couple of other processors say, hey, I want to get in with this group, they'll form links. And that's how little coalitions will form and all that. And so we're seeing this as a very good structure for artificial general intelligence by not having a central executive that's going to direct information that's omnipotent. We don't want that at all. Okay, so that's it for me right now. And we're going to go into Manuel, so oh yeah, so finally I want to say, this is a simple mathematical model. Our goal is to freeze the model and explore it, determine the good and the bad, keep it simple, make no unnecessary changes. We don't want to add things. Everybody's telling us about bells and whistles. We don't want to do that now unless we super have to do it. So that's what we want to do now, explore what we can do from this model.
Okay, yeah, thanks very much. Wonderful talk.